Hello, we are Team 30. Our topic is multi-label classification of competitive programming problems. Let's start with introduction. Our topic is to develop a tool that can label competitive programming problems. Many online judges have their problem unlabeled or have very inconsistent labels. This will make it harder for users to navigate on the website since they can quickly filter problems by topic, approach, or data structure they wanted to practice. And sometimes labels can also give a hint on how to solve problems. In addition, this tool not only benefits users, but also problem composers. They can use our tool to quickly give labels to their new problems. Our tool requires the description of problem as input. Usually, competitive programming problems have several labels, so our tool will output multi-labels that the problem should have. There are two related work. The first one uses CNN and use programming technique and data structure in accept solutions to recommend problems that is similar to input problem. The second one uses different pre-trained models like LSTM, BRTOL, MAA to predict text.
Let's move on to our dataset. So on the internet, there are not a lot of competitive programming websites that have huge problem set with good labeling, but one of the most popular ones are Codeforces, LeetCode, and SPOJ. Codeforces and LeetCode have datasets available on Hugging Face, but SPOJ doesn't, so we decided to implement our own scraper to collect all the problems data from this website. So one of the problems that we faced during a collection of our dataset is that all of these websites, they have different problem structure. For example, Codeforces may have input format, output format, but LeetCode doesn't have it. And also problem description style is different on all of these websites. LeetCode has a very straightforward description and usually very short, but Codeforces and SPOJ often have some storytelling, and this might affect model's precision. So in the end, we decided to have this dataset structure. We have only 4 columns in our dataset. First is the source, which can be Codeforces, LeetCode, and SPOJ. Second one is title of the problem. Third is description. We concatenated all of the sections in the description of all of the websites. That's input format, output formats, node, problem description, task description, and all other sections. We just concatenated them, and we got single column here. And the last column is the labels, which is array of strings of the labels for this problem. We didn't include examples, input and output examples to our description because these are often just random numbers or symbols which doesn't usually tell anything about problem tag. So about SPOJ scraper that we implemented, SPOJ has 4,000 problems, and that's almost 10 megabytes of data, but we cannot include all of the problems into our dataset because most of the SPOJ problems are labeled by the community, and these labels they may have very bad accuracy. So we decided to take only the most popular problems from the SPOJ to our dataset. Another problem for our dataset was that problems labeling across all of the resources is inconsistent. They have different naming, and also they have different structure. LeetCode has 71 labels, Codeforces 37, SPOJ has more than 200. So our solution was to prepare a list of standard labels and map all of the labels from this website to these standard labels. Some of the labels, sure, they didn't match any of our standard labels, so we decided to discard problems that have no standard labels. So after we did that, we had our dataset, and we decided to do some statistics to get some statistics from this dataset. So you can see that most of the problems, they have 1, 2, or 3 labels, but still some of the problems have 4 or 5 labels. And most of the problems are from Codeforces because this is the hugest problem set available online, and then LeetCode, and then SPOJ. So number of problems is more than 11,000, the word count is more than 3 million words, and dataset size is 21 megabytes. This is the description length distribution across all of the problems, and most of the problems have less than 3,000 characters. This is number of problems per label, and you can see that our dataset is very imbalanced. Some of the problems text, they are much more often occur than others. So we had to deal with that during the training. Let's see our baseline. We decided to use 1V stress classifier with logistic regression. This is a statistical machine learning model for multi-labeling, and it assigns labels depending just on the keyword, so it doesn't understand the context of the problem. So in the essence, we decided to use TF-IDF vectorizer to convert text into numerical features. 1V stress classifier is a strategy to train some model for multi-labeling, and logistic regression is a classification algorithm that's used to predict binary outcome. We also assigned class weight balanced to deal with our imbalanced dataset. And the architecture is kind of that. So 1VSRS creates a lot of logistic regression models, and for each label a logistic regression model is created, and for every problem it says if it has this label or not. So why we have chosen this baseline is because our baseline in its essence is a pack of shallow linear classifiers. Its feature space is like sparse back of words, it has no context understanding, it completely ignores words order. And our proposed solution is a transformer based model. Fine-tuned DistilBERT, it can capture semantics, understand context, it can do reasoning to some context. So the reason of this baseline is to compare how much transformer based model can do better than simple statistical plus machine learning model.
Hi, I'm Shishu Wei, and here's our main approach. We use DistilBERT as our main approach model. DistilBERT is a lightweight model distilled from BERT, which has less parameters than BERT, but it can still maintain the most of performance than BERT. And here's our main approach architecture. First, we will introduce the changes and characteristics of our task that shaped the approach. There are three challenges and characteristics. First is label imbalanced. Labels range from 250 to 3,500 samples. This can bias the label to a frequent text and hurt generalization on real text. And following is long inputs. Most problem distribution contain 1,000 to 2,000 words. Key classification information, such as I/O information and constraints, may be lost if we use default truncation, which simply keeps the first max length tokens and discards the rest. And the last one is label correlation. Certain texts frequently co-occur, versus, for example, graph and shortest path, indicating semantic dependency between labels that should be modeled. And here's our fine-tuning. First, we will add arguments for a better training process. We use learning rate, controls training speed and stability, and the weight decay prevents overfitting by regularizing large weights. Both are crucial for optimizing model performance. And we used iterative stratification from scheme multi-learn to split data, preserving both individual label frequencies and co-occurring label pairs with order 2. This ensures better distribution of rare and correlated labels across folds, reducing validation bias. And following, we use high token limit to deal with the long context. To retain more problem distribution, we set max length 512, which is the maximum token length supported by the DistilBERT. For input exceeding this limit, we applied head-tail truncation with a 0.5 ratio, preserving both the beginning and end segments of the input. And following is the weighted loss, which deals with the imbalance handling. To address label imbalance, we applied label-wise loss weights based on the inverse frequency of each label. And here's our formula. First, we will use negative and positive ratio, and we will use log to smooth it. And finally, we will clip the weights into the 1 to 10 and normalize to 0 to 1 to prevent extreme weights. And finally, we used PMI best of labels, which deal with the label correlation. Construct a label. First, we will construct a label occurrence matrix and compute the point-wise mutual information based on it. Generated soft labels for each sample based on its labels, PMI-based labels. Help the models learn the relation between labels. Final label will be like following formula, with sparsely filtering. And the gamma can sharpen the soft distribution. And why we use sparsity filtering is because we thought the value under 0.2 may be considered as a noise to our model, so we just zero out.
So here's our evaluation metric. So usually for the multi-labeling problems, these metrics are used. The first one is the F1 score. It's the combination of precision and recall of the labels. They are calculated in this way. And in our model we use two metrics, F1 micro and micro. Micro is the average F1 score among all the labels, and macro is calculated globally. Another metric that we use is the Hamming clause. Hamming clause measures the fraction of labels that are incorrectly predicted, either missed or incorrectly assigned, and is calculated in this way.
Here's our experiment part. First, we'll introduce about our experiment setup. The fixed set will be set into the training arguments equal to 32 to ensure reproducibility, and the matrix logged and visualized using TensorBoard. And our evaluation criteria is highest F1 score achieved. Early stopping is applied if the F1 score doesn't improve over the last two consecutive epochs. And here's our three types of experiments. First is learning rate, the second is number of tokens retained per sample, and the last one is proportion of soft vs hard labels. By default, the hyperparameter will be set like this. And first experiment is learning rate. For 1e-5 is too slow. It seems like underfitting and delayed F1 improvement. For 2e-5 is best overall. It's stable training, smooth validation, strong F1. And for 3e-5 is fast learning initially and highest early F1 score. Get a highest early F1 score, but it risks overfitting, like the steps between 3,000 to 4,000 steps. And for the number of tokens, for the 128 tokens, it underfits badly. Too little context for meaningful learning. And for 256 tokens, it's moderate results, slightly worse generalization. And for 512 tokens, it's best performance of all. It has stable loss and highest F1 score. And for the last experiment, the proportion of soft versus hard labels. The alpha equals 0, which means it's just the pure hard labels. It gives the best result in both loss and F1. And the alpha equals 0.3, which means the 30% of hard label and 70% of the soft label. It lists the unstable and poor generalization. And for the alpha equals 0.7, which means the 70% of hard label and 30% of soft label. It improves over 0.3, alpha equals 0.3, but still underperforms compared to alpha equals 0. And here's our key finding in our experiments. First is learning rate should be carefully chosen, not too large or too small. And second, we should use as much content as possible, with the token limit of 512, including more of problem descriptions significantly improve model understanding. And last one, PMI may introduce noise. Despite testing different PMI weightings, the F1 score consistently stayed below 0.5. So we concluded that the PMI should just be the noise to the model. Cannot help the model learn the meaningful relationships. Here's our result part. For result part, we will compare the precision recall F1 score per labels, and we can compare with the number of problems of them. We found that the labels that have small number of problems, they will get a low F1 score mostly. But there's an interesting note. Even though label interactive is the rarest label in our dataset, it has the highest F1 score. That's because the interactive problem's description is highly distinguishable. And here's the score between baseline and the distilled BERT. We have a conclusion that results of distilled BERT are just slightly better than baseline, even though distilled BERT is good in context and semantics understanding. However, results shows that it doesn't help to produce better results. Without the limitation, there are three limitations for our models. First, distilled BERT cannot do reasoning. After analyzing the results per label, we conclude that low F1 score is the result that context understanding doesn't play much role, but the model that could understand how to solve the problem may produce much results. And following is the low compute power. Training much large model as distilled BERT with dataset equal 512 requires a lot of compute power and take a lot of time. and the last one is probably not large enough dataset. Even though we collect in our chain dataset almost all available good labeled problems available in the web, maybe that wasn't enough. And here's our practical use.